Hi, this is a quick video to go over the use of Solver in Excel to solve titration curves analytically. In class, we went through the calculations, the equations that sort of dictate a theoretical titration curve. So we talked about alpha, which is the fraction of the boric acid in the conjugate base form. And as would be expected, that starts out very, very small and rises to close to 1 over the course of the titration. And that alpha is really just based on the Ka and the concentration of hydrogen ions, so that observed pH. Phi is basically where we're at in the titration in terms of the equivalence point. So we start out very close to 0, and a value of phi equal to 1 is your equivalence point. So this is telling us that based on pH, we reach that equivalence point somewhere between about 12.2 and 12.5 mils of base added. And phi also is just based on theoretical values, like the alpha value, the observed hydrogen and hydroxide concentrations that are based on the observed pH, and then the known concentration of base and the estimated concentration of acid. Then finally, the theoretical or calculated volume of base added. This is kind of a back calculated value that's, again, just based on sort of these measured or theoretical values excluding that volume of base observed. So this is a value, yeah, it's based on our measured and known concentrations and volumes of acid and titrant, and then that phi value that's really just based on pH and pKa. So we're back calculating how much volume of base was added, and that even with our estimates here, that matches up pretty well with what we observe. And you can see that in our curves as well. They're kind of right on top of each other. But what we want to use Solver for is to really key in on these two values in yellow. The unknown concentration of boric acid, we're guessing it's about 0.05, and the unknown pKa of that value, which is really truly unknown, especially since we added different amounts of mannitol to change the pKa. But that estimate of pKa can come right off of just eyeballing your titration curve. Okay, so now let's use Solver. The idea with Solver is that we're going to define this residual, which is the difference between the observed volume in column A and the calculated volume in column G. But also in this calculation we have a weighting factor. So you can see that it's the difference between the two volumes squared times what's in column H. And the weighting factor is really just to kind of make some points along the curve more important than others, specifically the points near the equivalence point. So to calculate that weighting factor, we just take essentially the slope of the titration curve. That's just kind of a stand-in for which points are more important, and we would expect to see the highest slopes at the equivalence point. So yeah, I've got just my differences of pH over my differences of volume, and that's really just a rise over run calculation. Now if I drag this formula all the way down, I see a couple of things here. First of all, this first point is kind of weird. This is not a particularly important point on the titration curve, so I would actually just, if you've got a kind of weird number here because maybe your pH meter was just took a kind of value that may be lower than what you would expect, I would actually probably just replace this with a number that's more in line with sort of some of the other points nearby. So I'm going to just change this to 0.5. This weighting factor is really optional. It's not terribly important. Then we do see our greatest values at the equivalence point. I see 0.6, 0.7. With your mannitol additions, you would probably see some greater values there. Then the other weird point is the very last point, and this one's really just kind of a sort of, it's drawing on zeros here in column A and B because of the way we have the formula set up. So I would actually recommend just typing over the formula and just use the value from the cell before. So I'll use 0.06. Okay, so I have my weighting factors. So then the residual, yes, the difference is squared times that weighting factor. I can drag that formula all the way down. and that's showing me the differences between my calculated line and my observed line, my observed titration curve. And then finally, we're going to sum up all of those residuals in this yellow box up here, I2. So this is just the sum of all the values in that column. And I also have this box in blue here that says, that's labeled original. The value in the yellow are going to change, so in cells B5 and B6 and I2, these values are going to change, so it doesn't hurt to just record what your initial values were, just so you have something to compare to. Okay, now at this point I would encourage you to save. The solver function, at least on my computer, my version of Excel, can be a tiny bit buggy. I sometimes have to, I've started it and then it kind of freezes and I have to restart Excel. Let's hope it works right now. So once I've enabled it in Excel, on my machine you have to go to Excel add-ins and then you can click a radio box for solver. Once I've done that, it does appear under tools. So to use solver, the first item here, it says set objective. So what's the objective? We're looking to minimize this value, which is the sum of the residuals. So I'm going to click on that box there. And we want to set the objective. We want to set those residuals, the sum of residuals, to be the minimum. So I've got minimum checked here as well. And then it says by changing variable cells, and it's got a box here where you can select the cells. Yeah, I want it to change the unknown concentration of boric acid and the unknown pKa of boric acid to get the best possible fit of that theoretical titration curve to the observed titration curve. And that's all there is to it. Let's see if it works here. You then get this little box that says keep the solver solutions or restore the original solutions. Before I click OK, I can just note here that my residuals have dropped. It went from 6.13 to 3.57, so that's showing me that I have a better fit now. And you can see that these values within boxes B5 and B6 are also changed. So I'm going to hit OK. That's why I kind of recorded my original values that I had there. But yeah, now my line fits even better than it did before. And the titration curve, the orange titration curve, is based on the theory, these fundamental equilibrium equations that guide what happens during a titration, including also the mass balance that we derived in class. So this is how titrations should act, and it's a bit of a more theory-based way of determining the equivalence point that doesn't rely on me having gotten that little drop of titrant in the flask at the exact right moment so that I hit the equivalence point right at the proper time. So for that reason, it's a little bit better than just kind of estimating or interpolating between 2 points.